You were what I was telling. So you were saying about like how to measure the mutual coupling, right? Hello. Okay. Okay. So let's say these are two antennas. So one is let's say these are like basically you can define this. Let's say the antennas are like the like this is let's say this is port one. So and this is port two, right? So now you want to you want to like measure what is what like uh, you want to find the coupling, right? So between two, let's say this antenna is transmitting and you can yeah uh, mm-hmm, uh, uh-huh, mm-hmm, hmm, hmm. Yeah, so then what uh, mhm, mhm. Mm, yeah, so actually, so basically, like you can, so basically, like, so you want to basically like, like the problem is basically just like your how much power. Let's say you are transmitting some power. Let's say some power at this port, and you are receiving some power at this port. So basically, your coupling is your power at your receiving antenna divided by your power at your transmitting antenna, right? So that is only there, right? So yeah. Hmm. 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 Mm, but like there will always be a loss actually. Hmm. 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 What is M upon? Okay. Hmm. Okay. Hmm. that is very simple actually. Like that that conversion is already very standard actually. So you like that so basically you are trying to convert basically like this coupling actually you can model with this transformer actually. Like you search that transformer model of high frequency circuit actually. So all this like whether it is inductive coupling or capacitive coupling depending on which region of frequency you are operating, that you can just model by RLC and RLC plus transformer actually. The loss you can measure a loss you can I think resistor, capacitor, and inductor. So basically, the coupling between let's say two different component you can model by either capacitor or inductor, and loss you can model by resistors actually. So I think like there is if you can go to like this poser microwave engineering in that like that this RLC model is given actually, so you can model your system. So you can write so basically your network parameters are written best in terms of if you are considering series or parallel connection. Like that depends on basic how you are modeling your system actually. If you are modeling your system as series RLC circuit, then your Z parameters are best actually. Then basically you can just use the Z parameter. And if you are modeling by parallel RLC circuit, so like this resistor, parallel capacitor, and parallel inductor. If you are modeling like this, then your best parameters are admittance parameter. Then you need to convert to admittance parameter. I can give you a reference. I think you can go through this microwave engineering by Poser. In that, basically, let me just what is the chapter? Uh, so yeah, Z parameter. Yeah. So you can go read this chapter actually. Microwave resonators, I think. So then, or in that actually a model is given. Or one more, I think one more book is there, like Communication Electronics by J.K. Shawnee. Like I can give you exact name in next class. I have it in my room. So that in that actually it's given a very detailed actually. How to let's say. Hmm. Oh, okay, just so basically, let me just give you like the way which in my system we find the coupling. So I'll just give you uh, uh, my screen is visible, right? Okay, just let me close this. So, ah, so basically, like so. Yeah, so my system is like that. So basically, it's like the this is the coupling loop. So here this is the uh, coupling loop. which is like coupled to this cavity actually. Like this is the cylindrical dielectric resonator cavity. This is air gap coupled. So this you can model. So this is I think similar to your problem. Basically, you are trying to couple two antenna. I am trying to couple loop with the cavity actually. So basically, this you can model with this all the Z parameters, and you can interconvert also. Like this C figure, this is a series RLC, and then you can couple the parallel RLC also. So that basically you can just model this system as a RLC circuit, like this whole this let's say this loop is coupled to some kind of resonator, and that system basically you can just model as a RLC circuit actually. So that basically once you like find the s parameters, then you can just convert to z or y parameters, and you will find your like you can analyze in that, like just by simple RLC, either parallel or series circuit. Yeah, because because like as you vary the distance between two antenna, your coupling will get impacted, right? So that modeling you need to take into account actually. So even in my case, so like that coupling basically, if I consider like inductive or capacitive coupling, so my whatever the modeling L is a function of loop area, distance between the like coupling loop and the cavity, and those other some parameters like what is the frequency and those things. So whatever the parameter equivalent parameter you will get will depend on your distance between your between your two antennas and those things, and how even the polarization of those antennas also will matter actually, right? So that those models you need to take around. Suppose your polarization mismatch is there. Yeah, it's very standard. It's very standard actually. It's given in this microwave engineering. If you go, it's let me just give you page number exact. Uh, it's very standard. Yeah, so you go to this microwave engineering by Pozar 192 page number, and this is I think fourth edition. Okay, so is that clear? Uh, this like David M. Pozar, 192 page number. Yeah, all the conversion. table is given actually. Yeah, I think it's all right now. Okay, I think I hope this answered your question. Really. Okay. So yeah, I think let's just yeah. So let's just uh, so let's just start solving the problem for this week. So the first problem is for a two-port network to be reciprocal. Which of the following is correct? So for S parameter matrix, reciprocity condition is S12 equals to S21. So the correct answer, the for detailed derivation of this, you can go through the lectures in the class for this week. So this was just a reciprocity condition you can try. So the I hope this is very straightforward question. So let's move to next. If your network is reciprocal. Uh, yeah, reciprocal or symmetrical, I think. Symmetrical is difficult term. Like symmetry, you can't define like reciprocal means suppose you give like you give from excitation from this response at this once you give response excitation this response at this so this is known as the I think symmetry and reciprocity may be same I don't know I will yeah so that condition is just like you can drive for detailed derivation you can just go through the class and if you have any confusion then just let me know in the next class. So next, let's move to next problem. If the port parameters is lossless and reciprocal, then what is the magnitude of S12? And if the magnitude of S11 is one, so the meaning of lossless is basically you won't have any loss. So the condition is given as derived in the class the S11 star plus S12 star equals to 1 or you can write as mod of S11 square plus mod of S12 square equals to 1 and basically you can get the in this question only the magnitude is asked so this is the sufficient condition to get the magnitude so you just basically you can get the magnitude of s12 just by s12 mod square is equals to 1 minus s11 mod square and that is 1 minus zero point 0.5 square and that is equals to 0.75 and if you take square root then you will get s12 magnitude as 0.867 or 66 something so the correct answer for this is near correct answer is fourth one 0.87 is that clear okay so then let's just move to next problem. So this is given as S11 is 0.316 and this is known as the voltage reflection coefficient. So basically it is V plus or A1 it is like the B1 by A1 and you can define that in terms of voltage. And basically, to convert this into dB, basically you take 20 log of mod of S11, and which is equals to 20 log of 0.316. And this, I think you will get, if you take logarithmic of 0.316, you will get around minus 10 dB. So the correct answer will be 10 dB, right? So this is the third problem. And so basically, next, let's move to next problem. Which of the following represent a unitary property? So that is, unitary is defined as your like your like this property, like S of transpose matrix multiplied by the complex conjugate of that matrix is identity matrix, or you can now unitary matrix. So that basically, like you can define as a, like the unitary properties is like the S is basically equals to S inverse actually. So and S inverse is your transpose matrix of the complex matrix. So that basically, like you can define as the unitary properties, and you will get from here, and the correct answer will be first one for the S parameter method. Detailed derivation is like derived in the class. So you can go through the lecture notes and let me know if you like could not understand any part or partial part of that. So let's move to next part. The next question. S21 of a line can be obtained by driving the input port and terminating the output port with. So basically, as we had seen, terminating the output with the let's say this is like the this is the line you want to match. So basically, the terminating uh, the output with the match load. Suppose the characteristic impedance is Z naught, and this is Z naught, ZL. So for matching, ZL should be equals to Z naught. So the terminating the output port with the characteristic impedance of your line. So that will be your correct answer. Is that clear? Yeah, Z naught. Yeah, that is very simple. So then basically, like which of the following is the correct relation between S and Y parameter? So let me drive this. So you can write the this V as a a relative voltage, like reflected and transmitted voltage A and B, and the I you can write as a minus B. So basically, scattering matrix you define as a voltage reflection coefficient or the voltage transmission coefficient, and those relative voltage you can write in terms of the actual voltage, and this is normalized voltage. And then basically, also one more equation is there. Your B is equals to the scattering matrix time your A, right? And like the admittance matrix, you can write as a admittance matrix as we have behind I equals to Y times B. So now we can replace. So if you this substitute B here, so we can write B equals to A times uh, S matrix plus A, and that A you can take common, then it will become unitary matrix plus S matrix times A. And similarly, you can define I as you. Yeah. So similarly, you can define I as unitary matrix minus S matrix times A, and which is equals to Y matrix time B. So that basically, so now basically you can write as a U minus S times A equals to Y matrix times V you can write as from here. So it is U times S plus A. So it is U matrix plus S matrix times A. So you can see like the this so if you compare from left and right side, so basically U minus S matrix equals to Y matrix times U plus S matrix, right? So now basically you can write as so basically like uh, you can so basically you can separate out these matrix. So basically so then U minus S is basically by minus, and basically now you can write as a uh, U plus S minus 2S, left hand side you can write as a Y times U plus S, and basically like if you multiply both side by U minus S inverse, so this first one will become unitary. So this so it will, if you multiply by U minus S inverse, then this U matrix plus S matrix times U matrix plus S matrix inverse plus 2 times S uh, U matrix plus S matrix inverse equals to Y matrix. Then basically like this will become again become unitary matrix U. Uh, so this will become U minus 2 times S matrix times uh, U plus S matrix times inverse equals to Y matrix. So that's how you can reach to the conversion, and the correct answer will be the second one. That's how like every like conversion you can do very efficiently. Like if it will take some effort in those like ABCD to Y and those conversion, but like the conversion is very straightforward and very standard. Yeah, so uh, like bit more practice and some intelligent adjustment of parameters, I think it should not be given in exam, but like at home it may be doable. Yeah. Okay, so then let's just move to next. I think it's clear, right? Like how I got, yeah. Okay, so let's move to next parameter. So next question. S parameters are valid for a definite set of reference plane. Which of the scattering parameters changes in the lossless network when the reference plane change? So basically, like as you see in the case of transmission line, suppose like there is a like reflection like let's say there is a finite reflection coefficient at some point here. Let's say that is gamma, and if you move L distance, then it changes by gamma by mod of gamma times exponential of minus j times 2 beta L. And for a lossless line, this is negative. So as you can see, the magnitude as you move along the line, so only the magnitude remains the same, only the phase factor get changed. So for a lossless line, lossless network, if you change the reference plane, only the phase will get changed, magnitude will remains the same. Is that clear? Okay, so basically, like, uh, so as like you can like you can like the reflection coefficient at any point you can define in terms of like the normal impedance times your reflection coefficient at if you know the reflection coefficient at load night side is gamma, then if the line is lossless, basically the reflection coefficient at other reference plane is just given by at some location L is given by mod of gamma time exponential of minus j times 2 beta L. So this is only the complex term, and if you take the magnitude of gamma L at any point, basically this term will go. Only this magnitude will always remain constant. Only the phase will get changed. Is that clear, or what is the doubt? So, uh, let's say this is saying S parameters are valid for a different definite reference plane. So now let's say you measured some parameters at some location of the transmission line. Now it's saying you are changing the reference plane. Now you are like shifting that reference frame to other frame. Let's say while defining this, this was the reference frame, right? So now it's saying like if I change this reference frame, what will get changed? Will the magnitude get changed or phase or both will get changed? So on yeah of our like the scattering parameters, all the reflection coefficient. So basically, if you change the reference frame, let's say you got some reflection like some S11 you got that is complex number, right? So then like once you change the reference frame, that S11 the magnitude will be get same, but only the phase addition will be there. So let's say some matrix is there S11, S12, S21, S22. So it's saying like let's say this you measured with respect to a certain frame. Now you change the reference plane. Then basically this only the phase time will get added into the scattering parameters. Other time will get remain same, particularly for the lossless line actually. For lossy line, it will get changed. Both the magnitude and phase will get changed. Hmm. Yeah. So this is that. So basically, like uh, so so let's move to next problem. Yeah, it's uploaded on YouTube. It will be uploaded. Link of that is there where the like the where the your login page is there, no? There the yeah. So, link will be given there. So then last I already updated the link for the last two sessions. Yeah. So for this network, uh, so yeah, so this network actually the for two port one network, what is the transmission coefficient? So this is basically so that basically like the forward transmission coefficient actually. So okay, so yeah, so for this network, basically, like what is the magnitude of the forward transmission coefficient if uh, Z11 equals to these are given. So what is the definition of in the so uh, so in this basically yeah, so this so ABCD parameters you can write V1 I1 equals to uh, ABCD V2 I2, and the so like the forward transmission coefficient is basically A, which is equals to V1 upon V2, given that I2 equals to 0. So I2 equals to 0 means like we have like open circuited this line. So basically, let's say you apply the V1 here, and this is because this line is open, so there will be no current. So V2 will be equals to the V2 at this terminal will be equals to here, and that, so basically you need to find the V2 by V1, V1 by V2. So basically how you can find, you can write in terms of like the potential divider you can write. So V2 will be equals to Z3 by Z1 plus Z3 times V1, and the forward transmission coefficient you can define as V1 by V2 equals to uh, Z3 by plus Z1 divided by Z3. So that will be equals to 1 plus Z1 by Z3, right? So so then basically like you can find this AB. This will be, you can like Z1 and Z2 are Z1 and Z3 are given. So that 1 plus J times J divided by 2J equals to, it will come at 1.5. Similarly, you can write B as uh, Z1 plus Z2 plus Z1 Z2 divided by Z3, and that you can write as 1 minus J minus J plus J times minus J divided by 2J, and it will be equal to minus 0.5 J. And similarly, C will be equals to 1 by Z3. It will be, so basically C is equals to your, C is equals to uh, C is equals to I1 by I2 when V2 is equals to 0. So so then basically that you can define as uh, 1 by Z3, and which will be equals to 1 by 2J, and it will be equals to 0.5J. And similarly, you can define D as 1 plus Z2 by Z3. If you calculate for this network, that will be equals to 1 minus J by 2J, and this will be equals to 0.5. So then basically you need to find the, what is the forward transmission coefficient actually. So then once you find this ABCD parameters, then basically you can convert to a scattering parameter S21. So the S21 conversion is there, A plus B by Z naught plus C by Z naught plus D, and that basically like this I did like I find the ABCD. You can drive this thing with Z also actually. So with normal Z parameter also you can like in that case basically you need to find Z to S conversion actually. Here I am doing ABCD to S conversion. So the answer will always be final, will be same, 1.5 minus 0.5 J by 50 uh, plus C. So it will be plus C times C is 0.5 J times 50 minus 50. So minus 0.5 J times 50 plus zero point 0.5, and basically that will be equals to it will be equals 2 by 2 plus 25.01 J, and if you take the 25.01 J, and if you take the magnitude of this, it will become 0.079. So this is S21. So I find this by ABCD. You can maybe try doing with the Z parameter actually. So the S21. Hmm. Uh-huh. Uh-huh. Yeah. No, no, no. No, no. Like, yeah. So any circuit. So that conversion is independent of circuit actually. So for this, actually, let's say you want to find the G parameter, Z parameter for this circuit. So how you will find? So let's say Z parameters is V1. So V1 equals to Z11 I1 plus Z12 I2, right? V2 is Z21 I1 plus Z22 I2, right? Now your Z11 is your V1 by I1, uh, given that your I2 is 0. So in this circuit, let's analyze what is the our Z parameter. So then basically your like these are these parameters, and basically your, so let's say this is Z1, Z2, Z3. So basically now you need to find V1 by I1. So if you put I2 equals to 0, like that means this outer port is open. So this port is open. So like this I2, this current is 0. Only this I1 current flows, and you have applied this V1 as an input. So only the resistance will which you will see this Z1 and Z2 series combination, right? If you apply KVL in this, so basically you can write V1 equals to I1 times Z1 plus I1 times Z2, right? Z3, sorry, Z3. So this you can write I1 times Z1 plus Z3, right? And then you can write V1 by I1 equals to Z1 plus Z3. So this is Z11. So yeah, it is calculated from the circuit actually. So now you apply Z this, you find all the Z11, Z12, all the four parameters you find, and then basically you just apply it to that. So Z22 you will, it will be by symmetry, you can see Z22 will be equals to Z2 plus Z3, and similarly you can find Z12 and Z13 actually, or Z21 also. So that once you find all the Z parameters, then basically you can just apply that conversion table actually, right? So it does not matter with, huh, huh. You just find the what is the relation between like the S21, you need to find what is the S21 related to Z parameters, right? And Z parameters you find, yeah, that is very standard. So let me just write like in terms of Z parameters, S21 is actually equals to so it is equals to so this is S21 is 2 times Z21 times Z naught, which is characteristic impedance, times delta Z, and delta Z is basically equals to, delta Z is equals to Z11 plus Z naught, Z22 plus Z naught minus Z12 Z21. So basically, now you need to find each of these term, and then you just plug in the z parameter value, and you will reach at the same answer actually. Yeah, S21 value, like the irrespective. Basically, like the depending on the network, I think you should solve with the parameters which is easiest to find for a particular network. So, for example, for this network, it is maybe very easier to find ABCD. Then you just first find the ABCD, then convert to S parameters actually. Yeah, yeah. So if you want final impedance, then you just go for Z parameter. Yeah, Y parameters. Yeah. Huh. Huh. A, B, C, D. Yeah. Mhm. Okay. Then basically, like, so, then, uh, let's just, so is that clear? No problem is clear, right? Okay. So, let's just move to next problem. For the two port network, ABCD parameters are A equals to minus 1, B equals to 0, B equals to 0. So let's write a matrix L. So, so matrix A, B, C, D, which will be equals to A equals to minus 1, B equals to 0, C equals to 0, D equals to minus 1. This is the ABCD parameters. So, you can write, you can write like the, you can find like S parameters. You need to find basically what is the like the reflection relation between input and output reflection coefficient actually. So that basically that you find by the S parameters, input and output reflection coefficient. So that basically first you need to convert from ABCD to S parameter matrix actually, and then basically you just convert like that S parameters to reflection coefficient. So let me just write those equation. So this uh, so uh, so the S11 is basically equals to A plus B by Z naught minus C times Z naught minus D divided by uh, A plus B by Z naught minus C times plus C times Z naught plus D. Let's call this as a row. So that basically A is given as minus 1 plus B is given as 0 plus C is given as 0, D is given as minus 1. Divide by, uh, so no, this is minus. Yeah. So this is yeah, this minus minus will become plus. Depend and in the denominator is minus 1 plus 0 minus 1. It will become so this top will get cancelled. It will become 0. So S11 will be equals to 0, right? And you can write S12 equals to 2 times AD minus BC by rho, and rho we find as minus 2. So AD is A is minus 1 times minus 1 minus BC is 0, and that because B and C are 0, divide by minus 2, and it will become minus 1. Similarly, S21 you can find as 2 by rho, which will be equals to 2 divided by minus 2, which will be equals to minus 1. And S22 will be equals to minus A plus B by Z naught minus C Z naught plus D divide by rho. and that basically you will put this equation. Again, you will find 1 minus 1 plus 0 minus 1 divided by minus 2. It will be equals to 0. And the reflection coefficient is given by the gamma 1 is given as S11 plus S12 S21 divided by 1 minus S22 S22 gamma 2 multiplied by gamma 2. So now we know all the S11, S22, all the parameters we know. So S12, S21s are minus 1, 1. S22 is 0. So S1, this is equals to 0. And this is equals to minus 1 times minus 1 times gamma 2 divided by S22 is 0. It is basically your S22 times gamma 2, and it will this term also will become 0. So bottom is 1 minus 0, and this minus minus 1 will become positive. So this final will be gamma 1 equals to gamma 2. So that you can find from this also, because this S12 equals to S21. So this network is symmetric, and your reflection coefficients are 0. So that means your like the reflection coefficient from 1 to 2 equals to 2 to 1, like because of the symmetry of the network. Is that clear? So basically, it's just about the conversion table. So from that, you can you can uh, calculate the parameters. Yeah. So the let's just move to next problem. Scattering coefficients of two parabolic network parameters are S11, and these are given. So this is 0, minus j 0. And two-port network is transmission lines of character Z naught is given as 50 impedance. What is its length? So, so you can write you can write in terms of for a transmission line you can write the uh, for a like the if you then basically S parameter metrics are given. So you can just convert to all the this S parameters for the D length transmission line is given as this one. So basically the transmission line S is given as cos of beta D times J's Z naught sine of beta D and minus J times by naught sine of beta D and cos of beta D. So if you you can write S21. So basically for uh, for like once you compare, this will be equals to your like the if you compare for like this like if you compare the coefficient basically, and this is basically the ABCD parameter. So ABCD parameters are given in this. You can convert to the scattering parameters, and for this line, actually, you will find that this will be equals to this scattering coefficient will be equals to for the lambda by 4 transmission line. Actually. So the length of line you can compare for this sine beta beta d term. You can just evaluate. Okay. So is there any confusion in the problem? So the correct answer will be a lambda by 4 line. So is there any confusion in this? Okay, okay, fine. Okay, yeah, just let me know if you have any doubt in the problem or okay, fine. So, is there any doubt? Like anyone else have any doubt for this today's session or next session? Then we can I will wait for some time. Otherwise, we can end this session for today. We will meet next week in the same time. Okay, so if there is no further doubt, just then end this session. Thank you so much for listening. We will meet same time in the next class. Thank you so much. Bye. Have a great time.